So today's lesson is on the derivative of sine, cos, and tan. So just sort of like the part 2 companion to yesterday. So again, it's just kind of looking at the similar things as yesterday, just reminding us about the quotient rule. So here we're asked to differentiate f of x is a numerator function divided by a denominator function, and we know that f prime of x would be equal to the denominator function times the numerator prime, subtract the denominator prime times the numerator. Again, it has to be in that order because the denominator prime must go with the subtraction. Oops. And then all of that divided by the denominator function squared. Okay, so you end up with that pattern. So again, just refresh yourself on that pattern. In our case here, the denominator function is sine x, the numerator prime is 1, the denominator prime is cos x, and the numerator is x, and then the denominator squared, again, just how to write this properly, would be sine squared x. Don't know if I can actually do this. Let's write it like this, sine x squared. Okay. For some reason I'm not in the equation editor. Okay, so it should look something like should look like that. There we go. Okay, so we have sine of x minus cos of x times x over sine squared of x, right? So you just, there's your derivative. Again, really useful to just take it into here quickly, take its derivative, and double check that, we got the right thing. Okay? Find the equation of the tangent at the given x value for the following functions. Okay, so remember, to do a tangent, you need the point, 0 and f of 0, and then you need the slope, which is f prime of 0. Okay, so to do this, let's start with the point first. A tangent needs a point and a slope. Okay, so let's solve the point first. The point would be f of 0, which is 0 plus cos of 0, which is 1. Cos of 0 is 1, right, because it starts at its maximum. So we know it passes through the point 0, 1. Its derivative, f prime of x, would be equal to 1. Now the derivative of cos is negative sine x. Okay? So f prime of 0, to remember what we're looking for here is the slope, is f prime of 0. So m is equal to 1 minus sine of 0. Sine of 0 is 0, so m is 1. So we are looking for a line with a slope of 1 that passes through 0, 1. Well, we know it passes through 0, 1, so that's its b value, right? It's y-intercept. So y equals 1x plus 1 ought to cover it. So let's try this one and just check. So cos x plus x. Okay, so there's x plus cos x. Again, the idea here is we're looking for a point. A equals 0, f of 0. So there's the point when x is 0. And then we go tangent AF, and it comes up with the tangent x plus 1, which is what we said, right? So there's the tangent that we needed. Okay, so one more tangent here. It's asking what is the tangent to sine x when x is pi over 6. So let's just remind ourselves here. We're looking for a point. That point is at pi. Copy pi from GeoGebra. See if that. Yeah. Okay. So pi over 6 and sine of pi over 6. And that point, of course, pi over 6 is the first angle on the way up for sine. So it's 1/2, right? So our point is pi over 6 and 1/2, right? So that's the value of sine pi over 6. And then we need the slope. M equals f prime of pi over 6. So f prime here is going to be negative cos x. Sorry, excuse me, not negative cos, just regular cos for sine. So f prime x is equal to f prime, of pi over 6 is equal to cos of pi over 6, which is equal to the square root of 3 over 2. So that's the slope. Okay. Now, what we know that the tangent is y equals mx plus b. And what do we know about that tangent right now? We know that the y value is 1/2 equals the m value, which is root 3 over 2, times the x value, which was pi over 6, okay, and then plus b. We don't know b, right? So let's isolate b. So b equals 1/2 minus root 3 pi over 12, right? Just make sure we understand that. So I did root 3 times pi on the top, 2 times 6 on the bottom, and then just shifted it over to the other side. We could take this line and clarify it a little bit. We could make this one over 12 and that one over 12. And we can just kind of create one fraction here. So the b value is 6 minus root 3 pi, all divided by 12. And therefore the tangent is y is equal to, root 3 over 2 x plus, and then this big fraction. So 6 minus root 3 pi I see. Oh, sorry, I get you. Okay, 6 minus root 3 pi over 12. So that's what I'm saying our tangent is, right? So let's go ahead and try to graph that. So let's draw the line sine x. So we'll draw the function sine x, I should say. Okay, so f of x equals sine x. We're going to plot a point, pi over 6, and f of pi over 6. And you can see where that point is here. It's at pi over 6 and 0.5. Might be beneficial to have the x-axis count in pi over 2's here. I can make this a little easier to see. Okay, so there's pi over 6. Now the tangent, AF, is that. Now, I don't know if that's the same thing that I did, so I'm going to do the same thing that I did. Of course, you could like check more decimals and then see if that works that way, but let's try and type in what we have. So we have root 3 over 2x, y, equals root 3 over 2x plus, okay, now our big thing here was 6 minus root 3 times pi. Actually think that's a mistake, but anyway. Okay, so there we go. So that's what I said the slope should be, or the tangent should be. And you can see it's a pretty good match. It's a perfect match. If we say intersect H and F, right, they intersect at that point, and you can see the tangent's perfect. It's above on one side and below on the other. So that's good. Okay, so there's our equation of the tangent. Okay. Determine the absolute extreme values for this function on the given interval. Okay, this is a really good question, one you should expect to get. To get the, so first of all, I'm going to notice that this is a closed interval. means we need to check f of 0, f of 2 pi, right? That's the beginning of the interval, and f of any critical points. Okay, so just looking at that equation, f of 0 is going to be 1. So f of 0 is equal to 1. The reason being cos of 0 is 1, sine of 0 is 0, so you add them together. And 2 pi is obviously the same value as 0 was, because it's a period of 2 pi. You'd be 1 period later, you'd have the exact same value. So now what we're looking for is the extreme values. In order to find that, we need to find the derivative. So f prime of x is the derivative of cos is negative sine, and the derivative of sine is cos. So we have negative sine x plus cos. We set this equal to 0, is negative sine x plus cos x, and that gives us sine x equals cos x. Now, this equation can be a bit difficult to solve if you don't remember how to do it. When you see an equation with sine and cos like this, remember one option you have is to divide both sides by cos x. Okay? And when you do that, what you get is you get sine over cos equals 1. And sine over cos, we know, can be replaced by tan. And, places where tan is equal to 1, well, think about your cast rule. Tan would be positive, so let's write this down. Tan is positive in quadrant 1 and quadrant 3. Tan has a value of 1 when x is equal to pi over 4, right? So again, you can inverse tan of 1, or inverse tan of 1 here will give you this answer, but this is a special angle, so you should probably recognize it. Tan has a value of 1 when x is pi over 4. So our quadrant 1 answer is pi over 4. Our quadrant 3 answer is pi plus pi over 4, right? Because that's how you move into quadrant 3. Okay? So so we have two answers here. X could be pi over 4, or x could be pi plus pi over 4, which we could simplify, which is also the same thing, as 5 pi over 4, right? That would be another place. So what we need to do now, we have two other candidates. So these two are candidates for the extreme values. So what we need to do now is we need to check the original function of pi over 4 and the original function for 5 pi over 4. Okay? If you check the original function, cos of pi over 4 is 1 over root 2, and sine of pi over 4 is also 1 over root 2. So let's do the first one first here. So f of pi over 4 is 1 over root 2 plus another 1 over root 2, because, oops, no, sorry, I see what I did. Okay, so 1 over root 2 plus 1 over root 2. So you get f is 2 over root 2. And then sometimes when you rationalize this, right, you can rationalize it. So we can go 2 over root 2, and then we can multiply the top and the bottom by root 2 over root 2. And I'm doing this to get rid of the radical in the denominator. So look what happens here. The two root 2's on the bottom cancel. They don't cancel. They multiply together to become 2. The top, you do top times the top, so you get 2 times root 2. 2 root 2. And the bottom is just 2. So now the two regular 2's cancel, and you're left with root 2. So we have a point here. The point is pi over 4 and root 2, which is 1.414, etc. Okay, so that looks like a good candidate for the absolute max because it's higher than both of the other candidates were. The other candidate we have is f of 5 pi over 4, and this one is the same as the one above, except in quadrant 3 my two values here for sine and cos are negative because sine and cos is negative in that region. So following the exact same thing as above, the whole thing is going to simplify into negative root 2. Okay? So the point that we're looking at is 5 pi over 4. 5 pi over 4 and negative 1.414, etc., etc. So the absolute, right, the absolute max is equal to root 2. Root 2. And the absolute min is negative root 2. Okay, and those would be the two values. This one occurs when x is equal to pi over 4. And the other one occurs when x is equal to, 5 pi over 4. Now again, let's have a graph of this one and make sure what we did makes sense and is right. So the equation I was originally supposed to draw was cos x plus sine x. So cos x plus sine x. I was only supposed to draw this thing from the, so let's draw function f between 0 and 2 pi only. So I'm only looking in this region right here. Okay? So when I go in here, I can see that what we said would be true is that 0 and g of 0 would be the point 1. 2 pi and g of 2 pi would also be the point 1. Then we said pi over 4 and g of pi over 4 would be the absolute max. And 5 pi over 4, 5 pi over 4 and g of 5 pi over 4 would be the absolute min. And you can see, you know, we got everything right there without needing the graphing software. We were able to do it just using our knowledge here from the calculus. Now, in this section, we're going to take the derivative of tan. We're going to work out a shortcut for doing the derivative of tan, and then you can start to do some composite functions that involve tan. And really, you know, the rest of today is just similar to yesterday, just with tan involved. Okay, so let's find the derivative of tan. Now, the derivative of tan comes from the identity that tan x is also equivalent to sine over cos, and therefore we could use a product rule, a quotient rule, right? Okay, so the numerator function is sine x, the denominator function is cos x, and the derivative, f prime, is going to be equal to, let's just quickly write out the derivatives for these ones. So, sorry, I just realized, I think this is double spacing on me. It's bugging me. Apologies. Okay, so the derivative of the numerator is a cos x. Cos x. Okay, and the derivative of the denominator is negative sine x. Okay, so now the derivative of the quotient is going to be, okay, remember, so it starts with d prime, it starts with n prime, cos x, then it goes to d, which is another cos x, then it's subtract d prime, which is negative sine x, and then nx, which is sine x. And then all of this is over cos squared x. Did I forget to close a bracket here? Yeah, I did. Okay, all of this is over cos squared x. Okay? Now, look at this for a sec and see how, obviously, if we have to do this every time, you know, we're trying to solve a tan inside of this, and I mean, like, we don't want to be going down that road. So look at this and try and think, what can I do to make this simpler? Well, let's start by saying f prime is, let's say, cos squared x plus, right, is two negatives. Then we have sine squared x, and then the whole thing is being divided by, just put brackets around it so I can do divided. The whole thing is divided by cos, sorry. Okay. There we go. Okay, so there you go. So there's what f prime looks like, cos squared plus sine squared over cos squared. Now, of course, the advantage to writing it this way is that we know that cos squared x, sorry, it's a real pain to write these things, plus sine squared x equals 1. Sine squared x equals 1. Okay, which means the top of our derivative can be replaced by 1, and we get 1 over cos squared x. Now, you are free to write this in a couple of different ways, but most of the time the way you're going to see it written, or you can write it as secant squared x, finally, or you can write it as cos to the power of negative 2x. But I actually wouldn't recommend this one because you might mix that up with inverse cos, but you could write it as like, sorry, let me write it this way. It'd be a bit easier to understand. So cos x to the power of negative 2. You can write it like that. So usually secant is the easiest one to do, but anyway, we've developed a quick shorthand here, which is that dy, so the derivative of y equals tan x is secant squared x. Okay? And let's just demonstrate that on GeoGebra quickly. So I'm going to draw tan x. I'm going to take its derivative, and it gives you tan squared x plus 1. But of course, tan squared x plus 1 is secant squared. It's the same thing. So that actually also is a very good way. I should write that one down too, is a really good way of taking the derivative. Let's write that down as well. Or tan squared x, tan squared x plus 1. That actually is maybe the best way of doing it, because secant, we don't really want to get into secant, I don't think, because you don't take the derivative of secant that easily, but you can take the derivative of tan again fairly easily. So tan squared plus 1, I like the way GeoGebra did it. Let's do it that way. So let's replace this. Let's go tan squared x plus 1. Now this is really interesting because usually when we take the derivative, the exponent goes down, right? But here you can see when you take the derivative of tan, the exponent actually goes up because tan squared x plus 1. Okay, so now the composite function. Okay, so how do you do the derivative when you have something inside tan? Again, we're going to do a chain rule. Okay, so y equals tan u, u equals 3x. dy dx is equal to dy du times du dx. Okay, let's just work out the chain rule. dy du first of all. Okay, so I have a tan u. I change it into a tan squared u plus 1. Okay, that's what the derivative of tan is, right? You change tan with tan squared and then put a plus 1 at the end. And du dx is obvious here, is just 3. So the derivative I'm going to get, dy dx, is equal to bracket tan squared u plus 1 all times 3. So I get dy dx is equal to 3 tan squared x plus 3. Okay, and that's the correct derivative for tan 3x. Okay, let's just quickly show this one. So tan 3x, and then its derivative, and it's 3 tan squared. Oh, I'm sorry. I also I forgot something here. You see, it was u. I forgot to replace the u. So u has to be you have to write it as 3x again. I just forgot to make that substitution, right? Remember, my substitution here has to be my substitution here because I can't leave the answer with a u. So there's my final answer. Okay, so in general, if you're taking the tan of a function, then what you do is you do tan squared x plus 1 in a bracket, all of it in a bracket, and then multiplied by the derivative of whatever was inside tan. Okay, just make sure the plus 1 is also being multiplied, and you don't just put the plus 1 at the end. The plus 1 has to be part of what is being multiplied by the f prime. Okay, so let's look at a couple here. I'll do as many as I can in the next few minutes, and I'll leave a couple for you. Okay, so here, the derivative is going to be, so dy dx is going to be tan squared of the function 4x squared plus 2x. Then I have a plus 1 for the fact that it's tan. So there's my derivative of the outside function. And then I just do the derivative of the inside function, which we can recognize as 8x plus 2. Okay? So there's the derivative for that one. I do the derivative of the outside function, which is tan squared blank plus 1. I copy the blank out exactly as it was, and then I do the derivative of the blank at the very end. Make sure the plus 1 is inside the bracket. Okay? Again, this is easily checkable on GeoGebra, excuse me. You have tan 4x squared plus 2x. I said easily checkable, but maybe let's just draw this function between 0 and 2. So it's not drawing so much. Okay, so there's our function. Take its derivative. Okay, 8x plus 2 is in the bracket. 1 plus tan squared is in a bracket. And then inside tan is the 4x squared plus 2x, exactly what we said. Okay, so that's that one. Here we have tan of sine x. Okay, let's do it in Leibniz just to keep us sharp on that topic. Okay, so Leibniz. Let u equal sine x. Then y is equal to tan u. dy du is equal to tan squared u plus 1. That's the derivative of the outside function. Now, du dx is equal to cos x because derivative of sine is cos. dy dx is equal to dy du times du dx, which is equal to, let's just write it down again, dy dx. Okay, so dy du, first of all, so put it in a bracket, tan squared u plus 1 multiplied by cos x. Now I look at my answer, I notice I have a u in there. I don't want a u in my final answer, so I write tan squared. I look back at my question, what can I replace u with? Sine x. Okay, then I still have the plus 1, and then I have the cos x multiplied at the end. Okay, and that's how you take the derivative of that one. Again, let's just use GeoGebra to quickly check. So this time I want tan of sine of x, and then the derivative is a cos x multiplied by 1 plus tan squared of sine x, right? Exactly what we said it should be. Okay, this one. The outside function, so let u equal, we're going to let u be the inside function. So let u, what's the inside function here? Let u, okay. Let u equal tan x plus cos x. Y, therefore, is just equal to u squared. Okay, if u is what's in the bracket here, then the outside function is simply u squared. dy du is therefore 2u. Pretty easy. The du dx, okay, so the derivative of the inside is going to be tan squared x plus 1, and that's the derivative of the tan part, and then the derivative of cos is negative sine x. Okay, and so I just replace it like so. So the derivative of y with respect to x is the derivative of y with respect to u multiplied by du dx. So we're just going to multiply all that stuff together. dy du is the first thing I'm going to write, is 2u. And then I'm going to multiply by du dx, which is tan squared x plus 1, take away sine x, like so. And then I'm just going to write, I'm going to replace the u with what it's equal to, tan x plus sine x. Bracket tan squared x plus 1, take away sine x. Okay, and that is our final answer. There we go. Okay, so a 2 tan plus sine in a bracket. Let's just change the color of the different terms. So that's the u. right? My substitution is there. The 2 comes in front, and it gets reduced to a 1, so that's fine. Copied out the u, and then here's my derivative of u itself, and this is coming from this part right here. Sorry. Okay, so there's the two parts as they're assembled. Okay, now this one is going to be a product rule. So a product rule, dy dx is going to be equal to 3. So I bring the 3 to the front, and then take the derivative of sine 4x tan 2x, right? So I'm going to take that constant to the front and then do the derivative of the products. So let's look at the products. There, let's call the f function sine of 4x. Therefore, f prime is equal to cos of 4x times 4. G of x, let's say, is tan 2x. Therefore, g prime of x, okay, so look at how this is done. Start a bracket, tan squared, copy the 2x, plus 1, then take the derivative of the inside of the bracket. You get that, okay? Now, let's put all this together using the product rule. Okay, the product rule, so we're going to keep that 3 at the front. Then we're going to do f sine 4x times g prime, which is tan squared at 2x plus 1 times 2. Okay. Then we're going to add the tan 2x, so g, and then times f prime, cos 4x times 4. Okay. Now, some of this is, I think, able to be factored. For example, they both have a 2 and a 4. So let's try and factor them now. So let's highlight some common factors. So a 2 from that term and a 4 from that term can be brought to the front. So instead of a 3 at the front, I'm going to put a 6. I have sine 4x tan squared 2x plus 1. Sorry, that all has to be in a bracket. Plus tan 2x cos 4x, and all of this is only multiplied by 2 now instead of by 4. Okay, now looking at the rest of this, it has a tan 2x and this one does too, but the tan 2x is in a bracket with a plus 1, so that's no good. Sine and cos don't really cooperate, so I don't think I'm going to bother with that. So I think I'm going to leave it as it is. Okay. So that would be what my answer would be for this one. Again, this one's fairly complicated. Let's check it, make sure we did it right. So I'm going to change my original function here to 3 times sine 4x times tan 2x, and the derivative it comes up with. So you can see it expanded the derivative. So I'm going to ask it to factor f prime. Still coming up with a 12. Okay, so let's look through and see what they're doing that's different than mine. So cos 4x tan 2x, so that's what we have on our side. Oh, you know what they did? They just I'm sorry. They don't have they just multiplied in the 6. So they did this. So they did 6 sine 4x tan squared 2x plus 1 plus 12 tan 2x cos 4x. So they just did like that. They just got rid of the common factor. They expanded instead of factored, which actually makes just as much sense here because we weren't really able to factor anything useful except the fact that you know, an integer or coefficient. So I don't think that makes a big difference. Either answer would be fine here. Okay. I'll do the I got enough time today, so I'll do the last two. If you don't want to see them, of course, I'm not going to say anything else today of importance. If you just want to do these two yourself, if you want to see them done, then you can keep watching for this one. Okay, so this one, y equals e to the tan x squared. Okay, let's go through a full triple Leibniz notation. Okay, so let's say r equals x squared. Actually, let's do this. So u equals x squared, r equals tan x. Excuse me. Sorry, not tan x, tan u. right? And then y equals e to the r. Okay, so do you see how the, oops, where was I? This one? I don't know. Sorry. Okay, so think about how this is being done. First, I go e to the power of r. Well, what's r? E to the power of, what does r say? Tan u. And what does u say? E to the power of tan, and then u is x squared. Okay, and that's the question I'm asked. So this is my way of packing it up using a triple substitution, right? So that's kind of like how you can just make sure that you're only ever doing one step at a time. Let's write our three answers. Du dx, the derivative of u with respect to x, is 2x. Dr du, which is the derivative of, of r with respect to u, okay, is, let's put it in brackets, tan squared u plus 1. Okay. Finally, we have the derivative of y with respect to r is just e to the r again, because we know the derivative of this one is just e to itself. Now again, how do you do a triple one? I want the answer dy dx, so everything else I have here has to cancel. dy dr times dr du times du dx. Now if you look, there's an r on the top and an r on the bottom that kind of cancel. There's a u on the top and a u on the bottom that kind of cancel, and you're left with dy dx. So you can do the chain rule as a 3. Let's put the 3 parts in. So let's make color coding here. So dy dr we'll put in blue, which is just here. Okay, so the first term I have is e to the r. Okay, and again, I'll put it in blue just so we can keep track of it. The next term I have, okay, says dr du. So let's look for, where do I have dr du? Put it in orange. Dr du is right here. Okay, so again, let's just copy and paste it. Okay, and then finally I'm looking for du dx, which we'll just put in red. And du dx was right up here. It was a nice easy one. Was just equal to 2x. And let's put it in the red color. Okay, so there's my derivative. Now, of course, I can't leave my derivative with a u and an r when I want it in terms of x. So I write dy dx equals, okay, e to the r. What do I replace r with? R was replaced with tan u. Okay, then I go tan squared. I don't want u. I want, what is u equal to? U is equal to x squared. And then I have the plus 1. And then I have the 2x. Now, looking back over this answer, I notice I still have a u in there that I don't want. So I'm going to take that u and replace it with what I know it's equal to, which is x squared. Okay, and there's your derivative there. Nice, one thing at a time from beginning to end, just knocking out each thing as a Leibniz rule. Okay, so again, you don't need to do a triple Leibniz if you don't want, but once you get the hang of this, I think you will actually find this is the easier method. It's just, you're very unlikely to make an error because you're only ever doing one derivative at a time. You're never doing the derivative of whatever. Now you can also do this in the chain rule. It's like I say, it's perfectly fine. I would accept that, so not to worry if that's the way you prefer to do it. Let's do the last one as a regular chain rule. We won't do it as a Leibniz, just to do a chain rule. So the chain rule says we're supposed to take the derivative of the outside function and then copy the inside function and then take the derivative of the inside function. So the outside function is something squared. So this little 2, the final thing to happen here is that it's being squared. So I'm going to bring the 2 to the front. I'm going to copy out the inside, tan 3x, and it's going to be to the power of 1 instead of to the power of 2, right? Basically, this is what happened as a first step. Now I need to take the derivative. I need to take the derivative of the inside. Now what's the derivative of the inside? Tan squared 3x plus 1. And then what's the derivative of the inside of that? The derivative of the inside of that is just the 3. Okay? So your final answer here is y dy dx, or y prime we can just say, equals, okay, 6 bracket tan 3x bracket tan squared 3x plus 1. Now you could expand this if you want. Y prime is equal to, so 6, then we're going to have tan cubed 3x plus tan 3x. I don't think that's actually useful. It's probably better to leave it the way it was in the previous step. So actually, let's just strike that through. I don't think it's wrong, but it wouldn't help you solve, right? It'd be easier to solve in the one above. It's not wrong, but let's just leave it the way it was before. Okay, let's try this one so I know I'm telling you the right stuff here. So tan squared times 3x not times 3x, tan squared of 3x, excuse me. So you get 6 bracket 1 plus tan squared 3x, and then tan 3x. Yeah, okay, good. So we have everything there. Okay, so that's it for today. You could see a lot of this skill is about taking the derivative. You need to know how to take the derivative of sine, cos, and tan for the test. Any questions, please post, and be ready for a day of review and then the test beginning after that.